is not something that you necessarily can extract, and you'll have to beat it down with regularization, and it will be something simpler than the underlying pattern. That is a very important thing to understand. We work with data, we're statisticians. We don't know the underlying pattern. And more often than that, we've just got a model of the underlying pattern, and the true data generating process does not look like what our model is. And it's very easy to mistake the model for the reality. And every time that happens, things go kaboom. Just study finance and you'll see that. Just to be more specific, in all of option pricing, the people who essentially invented the technology to price options stuffed it up because they believed the models over the reality. Okay, so don't do that. My other main gripe with this is that this theorem makes no claim about the efficiency with which it can approximate things. So fine, you can tell me, if you just use enough neurons, great. You can approximate anything. But why should you believe that your neural network will be easier to use to approximate something to a particular level of precision than a Fourier basis, for example? If you could approximate a wave function, a pretty complicated wave function, using, say, 5 to 10 sine and cosine waves, why would you want to use 600 neurons and 10 layers? This is what I'm saying. Okay. This theorem makes no claim about the efficiency with which such arbitrary precision can be achieved. Okay, so take the universal approximation theorem with a bit of salt, but it is a valid reason for why we want to use this, because it can approximate nonlinear functions. Okay. My other main reason I think that we really concern ourselves with these models is they're easy, well, the machinery is easy to sort of massage into something that we can use for many different problems that we work on. We can use these models for when we've got multiple outputs. For Fourier bases, that's not so easy. If you've got one output, Fourier bases, always try it. You might be surprised how often it works very well. If you've got multiple outputs, not so easy. This closed model can be used for continuous responses and categorical responses. So it's more practical reasons why we actually use this technology over some others. And then, again, if you're a good statistician, you'll probably try out many of these, depending on what the problem you're working on actually looks like. Okay. Cool. So any questions? Okay, and maybe just to give you some idea of how all this stuff is. Okay, so I argue it's a set of nonlinear bases. I need to teach you how to work with these nonlinear bases and to do it in the right way. But again, talking about, just to finish off the idea on hype and such, I started putting stuff together for this course like many years ago. And then as we were talking about this, I talked to Linda Haynes, said, I'm putting all this stuff together on neural networks, and we're going to do all this stuff from scratch. And I said, oh, okay, no, I've got some notes from way back in the day where I gave a workshop on neural networks. Look at that date. This is November 2, 1993. I was 5 years old, roughly twice as smart as I am now. But yeah, same sort of story. We've got the biological motivations for why these things are important. We've got all our activation functions and interesting things. Recognizing faces and talking about how many neurons there are in the brain. Artificial neural networks, test sets, supervised, unsupervised learning. Does this all seem familiar?
Yeah.
Okay. Cool. Network architecture. Emulating the brain does not imply brain-like capability. Sure. This is a rough history. We'll go through some of the history shortly when we talk about the perceptron learning algorithm. Lots of great stuff in here. Talk here about errors, forward pass, gradient descent, Oh yeah, we've got some regularization and smoothing. Bombed out, come on. Minimizing objectives, subject to a constraint, these kind of things. Multiple classes. Some conclusions, and then some references, which you will see rehashed now, because as you go through these things, you keep finding the same references because it's okay, so very interesting. Actually, a lot of the technology, very old. Very, very old. In fact, a lot of the ideas people use for this, it's like, okay, cool, this is a great idea to, let's say, use for option pricing in finance. Terrible idea. And unsurprisingly, a lot of this technology predates option pricing. So you'd think that someone would have used it then before inventing an entire field of stochastic calculus to figure that problem out. Okay. But why are we interested in that? So, okay, it is a useful class, nonlinear bases that you can use for almost anything. But I would argue that the main reason that we are so hyped about it now is accessibility, both in terms of compute. We've got cheap, fast compute. Back in '93, training these things, even for small problems, not so easy. Nowadays, you've got enough RAM on your phone to do pretty much anything. And I guess also software being more accessible than it was back then. Okay. Cool. Any questions about the history before we go on to the perceptron learning algorithm? Cool. Okay. So we'll start right at the beginning of everything with the so-called perceptron learning algorithm. Now we will also see some of the naming conventions. Okay, so perceptron may refer to either a simple neural network, as we know it, or a primitive type of neural network. When I talk about a perceptron, I actually refer to that very primitive thing. But in a lot of the literature that you'll run into, you'll see them talk about multi-layer perceptrons. What they mean by multi-layer perceptrons is what you and I would mean by neural network or artificial neural network. Okay. And all of this really starts way back in 1943 with Warren McCulloch and Walter Pitts, introduced one of the first artificial neurons. This is basically a weighted sum of input signals, which is compared to a threshold parameter, and then it fires off a 1 if it's greater than the threshold, 0 otherwise. Okay, so it's based on the idea of a neuron fire. Later on in the 1950s, Frank Rosenblatt, we'll revisit him shortly in our YouTube video. He developed a class of neural networks called the perceptron, which was similar to the Pitts network, but he had the addition of a learning rule, and we'll talk about the learning rule shortly. But roughly the learning problem was the following, similar to what we do in statistics now. You need to determine a weight vector that causes the perceptron to fire when it should. Essentially that's it. You need to identify the parameter or the elements that go into a vector which has that particular value. And then, yeah, along the way, basic models were sort of modified. So the perceptron learning algorithm has very sort of hard threshold of a fire of 0 or 1. Later on, they added softer discriminants, so that means like these activation functions, which were sort of gradual, so you can get a sort of level of an output, if you will. And that's, I guess, closer to what a neuron behaves like. But yeah, a good account of the history is given by this oak. It's Brian Ripley's text on pattern recognition and neural networks. Actually has very little to do with neural networks. He was smart to put the name neural networks on the book and then talk actual stats inside, which is great. This is a very important guy in the world of statistics, brilliant stuff. Everything from first principles, all the theorems and stuff you see, you can find in here. But also a lot of the history. So here's some of the history. And this is Ripley's one. So I always say I read from the Gospel of Ripley. So take it as the book. Okay, so a great deal. So this, by the way, the book was, I think, 2006, 7. So this is a bit later than Linda's notes. But this is, again, on another wave of hype on machine learning algorithms and neural networks. So he says, a great deal of hyperbole has been devoted to neural networks, both in their first wave around 1960, Woodrow and Hoff and Rosenblatt in 1962, and their renaissance from about 1985, chiefly inspired by Raman McClellan, 1986, so this is still before I was born. But the ideas of biological relevance seem to us to have detracted from the essence of what was being discussed, and are certainly not relevant to the practical applications in practical pattern recognition. Because neural networks has become a popular subject, it has collected many techniques which are only loosely related and were not originally biologically motivated. In this chapter, we will discuss the core area of feed-forward or backpropagation neural networks, which can be seen as extensions of the ideas of the perceptron. From this connection, these networks are also known as multi-layer perceptrons. Okay, and then they talk a lot about the history and where these things and then they actually give a biological motivation. They give you some differential equations, which are better models, if you will, for how neurons actually function. Okay. But yeah, that's roughly the history. So again, you see lots of these ways and lots of similar problems and things throughout. A lot of hype around these things, and then we get lost in the metaphor, which we use to actually explain what these models are and what they do. Functionally, what they are just nonlinear bases, which can model inputs and association structures. Now, the simplest case of a neural network is the perceptron. Again, very simple mathematical structure. So the perceptron learning algorithm, really basic stuff. You have a vector of inputs, okay, like you would be used to, and then you would say, if you take that vector of inputs, you multiply it by a set of weights and you add them together, so xi transpose w, that's that summation. If it exceeds the threshold, then it's class A. If it doesn't, then your prediction is class B. Really as simple as that. A way to think of this, and how it's often communicated, is that xi transpose w is just the summative score of that particular input vector. So remember, in your input space, you've got this high dimensional space. Your observation is a coordinate in that space. So what is the vector w doing? It's scoring that coordinate, likelihood of being either class A or class B. Okay, and that can be just whatever value, as long as it exceeds the threshold. Okay, we can then associate the particular outcome, if we have examples of those outcomes, with each of those scores if we wanted to. Okay, come back to the learning algorithms. So mathematically, another way to write this down, or at least more formally, we've got the vector. We can't just say class A, class B. We need to encode that as well. So we encode the responses as being plus or minus 1. So usually we would encode binary responses as 0 or 1. Often it is convenient to use -1 and +1 to indicate two different classes. And here's an example of where we do that. So xi transpose w is less than some threshold, and here we define the actual threshold. In all of neural networks, this would be referred to as a bias term. Okay, so we've got some b there. If that vector in a product is greater than that threshold, +1, if not, -1. And there you go. That's your model. And in fact, this function here is just the signum function evaluated at the inner product, okay, minus the bias. Okay, so you take xi transpose w minus the bias, plug that into the signum function, and then you get what? A -1 or a +1, depending on whether xi transpose w is bigger than the bias. Okay. So what is this mathematical model doing? It's mimicking that function that we said, okay, it fires or it doesn't fire. Hence, perceptron or neuron. Okay. Now, here this model is aimed at binary classification tasks. So if you've got two possible classes, another thing to note is it's a linear model. we simply take a linear score of those inputs, and then we say, again, that doesn't mean we can't model things which are non-linear. We can plug non-linear elements into that xi. Then we must just understand that our model is still linear because it is doing what? It's partitioning observations in a non-linear space. Okay, so in this high dimensional space. Okay, so fine. That's our model. How it behaves is entirely determined by its parameters. So what are the parameters for this model? Weight vector and the bias. Weight gives you what? How to sum up the inputs and give a score. Bias tells you what's the threshold. And the rest of the model is just signum function which says fire, don't fire. And that's it. Cool. So how do we get such a model to learn? How would you guys do this? Come on, you know a lot about stats and linear models. Yes? Okay, so you're thinking, okay, fine, we've got some data, we've encoded it as -1s, +1s, let's get an objective function and let's optimize the prediction somehow. Okay, fine. Can you see a potential problem with doing that? So what objective function would you use, for example? So if this is a classification problem? I heard something? What do you mean it's for neural net? It can be used for anything, right? Anything is classification. Right, it's just an objective function. When you use the sum of squares, does that tell you, oh, you can only use it for this? I'm married to this model, sorry. No. You're right, you can use that as an objective, but can anybody see a problem? So you've got an objective function, where are you going to plug that objective function into? Some optimizer, right? Okay, now you've got this objective function, you've got your optimizer. Can anybody see potentially anything going wrong?
It optimizes for what you put in.
Okay, it optimizes what you put in, but what do you need to train? You need to train W and B. So you need to optimize with respect to that vector W and B. Look at that function. So your objective, yes? Definitely not differentiable. Also, look at this activation. It's flat there. So, for how many values of W and beta, what regions of the parameter space will this thing look exactly the same? Huge regions of the parameter space. So, your training algorithm is going to say, plug this into our objective function, change the parameter as follows. And then it changes the parameter by a magnitude. And then if it doesn't happen to cross the threshold, what has changed? The objective has not changed, which means the gradient of the objective function has not changed, which means your optimization routine is going to say, excellent, we found a minimum, return. To which you, as a good statistician, your bullshit text is going, this is rubbish. Okay, fine. So these guys, all the way back in the day, they understood this, and they were very clever. So they came up with the following. It's called the perceptron learning algorithm. And I'll show you the connection to some updating algorithms shortly. Okay. So our function just evaluates signs. We need to figure out how to find W hat and B hat in this model. Fine, it's this nonlinear thing. How do we do this? Well, enter the perceptron learning algorithm. So first, we initialize, we make a guess for the weight vector, and whatever it is, we don't know what it is. This algorithm is going to find the weights for our. It gives us the behavior. Okay, we start with our guess, then we iterate. How we do this is we pick an element at random from the set of labeled observations which is misclassified by the expression. So we have our initial set of parameters, we can evaluate the model, check which observations are misclassified. From those which are misclassified, then you say, take the weights, whatever it is now, add yi star, I star is the one that you selected. So this is going to be plus or minus 1 times the vector. which is the input, I star, for that misclassified. So you look at one observation and you just subtract or add the vector component. And that gives you your new W, and you're going to keep iterating. Okay. Eventually, if you manage to perfectly classify the data, your algorithm stops, and then it returns the weight vector, whatever that might have been. Okay. Okay, so notice just here, just one quick comment. There's no bias term in here. The reason there's no bias term in here is we've hidden it in the vector W. So note that X transpose W minus B can be written as just X transpose W, where you've added a 1 in this vector. So you'll have seen this before in linear regression. Remember, the first column you add is a column of 1s. That's for the intercept term. Same thing, bias. Okay. So if we subsume that bias in that vector, we can apply this algorithm and it'll work, and we just say that the parameter is in there, in that W vector. Okay, so everything we need is in this W vector. Sure. Okay. So that seems a bit arbitrary, right? So you just pick the observations which are misclassified, add or subtract whatever the input for that is, and then you keep going. So why would that work? Why are you popping up? Let me show it to you on the, oh, you know what? It's because of the animations. Okay, so here we go. The geometric intuition behind the perceptron learning algorithm is very simple. It says that, well, that X transpose W is just the inner product between two vectors, right? So you take the inner product between two vectors, the sign of that inner product tells you something about how they are orientated, right? If you take the inner product between two vectors, and those two vectors are orientated like that, what is the sign of that inner product? Come on. Come on, don't be scared. Okay, so positive, and then it's like that.
Negative.
Okay, so if our model is taking the sign of an inner product, what is it just telling you? It's just telling you how they are orientated. Okay, so fine. If X transpose W is less than naught, but Y, the response is greater than naught, then it's misclassified, right? So we just need to modify W such that X transpose W is greater than naught. So we need to modify W such that the inner product corresponds to the output. Same thing for when it's negative. So a consequence of the algorithm is really that there's some plane, remember, X transpose W, when you look at a linear model, it's just the plane in the input space. Okay? This algorithm is rotating that plane in the input / predictor space such that it separates the data. Okay, and it'll keep iterating and updating to do that. Okay. So here you have the operation for the updating algorithm. You take whatever the weight is before, okay, and then you either add or subtract the input vector. Okay, and whether you add or subtract is determined by the response, the yi being plus or minus 1. Okay, so here's an example. So if you observe before that the response is negative and your predicted response, so the inner product is plus 1, okay, so it's something like that. So that's W before, that's the observation. You want the prediction to correspond to the observation. So you want this thing to be like what? Open, right? So what does the operation of that do? Here's the operation. Here's what that vector looks like after you've taken this W and you've subtracted that. So take this vector, subtract it. Where does that put you? Over there. Okay, now, however which way that thing is orientated, you can see what the effect is going to be. Okay. So in W4, it's positive. You can always make it such that that inner product is negative. Say it the other way. Okay. So that's a geometric interpretation of why this algorithm actually works. Okay, some interesting things about this algorithm. The algorithm is guaranteed to converge to a solution if the data are linearly separable. So if we know the data are perfectly separable, it will find an answer. Problem is that's going to depend on how many observations you have and the dimensions of the data set. It can be quite slow depending on what your dimensions are for your data. But yeah, very interesting algorithm. It also only uses one observation at a time to modify that vector, so not particularly efficient way of learning. Remember, there's not a lot of information in a single observation. But yeah, fine. It can still be used when your data are not perfectly separable. Okay. What you do then is you say, fine, I'll just let it run until it achieves a particular level of accuracy, and then you pick the best solution that you've seen achieve that accuracy. That's the so-called pocket algorithm. So you run it until you observe, say, 95% accuracy, and you say, I'm good with that, and there you go. Another problem with this algorithm, solutions are not unique. That's not surprising. If you have data which are perfectly separable, okay, so if you have one class of observations here, another class of observations here, you're separating it linearly. Do you agree there are many lines that could separate that data? There are infinitely many. This is a problem that applies to logistic regression as well. This is not unique to this algorithm. But yeah. So that's the separate learning algorithm. It's perhaps the simplest marriage of a model, so we define a model, and then some learning rule to figure out what the parameters for that model is in a sort of pure machine learning way, purely data-driven way. We just have an input, we've got a model, and we want to predict something. And our learning algorithm tries to improve that prediction. That's it. No assumptions about necessarily how the data were generated. Okay, I guess we do have the implicit assumption that things are linearly separable, but you'll see shortly that that doesn't really matter too much. And yeah, so this is the starting point for the genesis of neural networks. Yes.
I'm guessing the reason why we use -1 instead of 0 and 1 is so the algorithm can actually work.
Yes, it's that subtracting of the, yes, it's very convenient to do that.
And does the magnitude affect, like the magnitudes of release of like 10 and -2, does it affect the performance of the algorithm?
Okay, you need to be careful now. So you're asking whether the magnitudes of those elements matter. Not so much. This again comes back to the problem of there are many weight vectors which will linearly separate the data. Not only are there many distinct vectors which will separate it, there are many distinct vectors, there are infinitely many vectors that look the same. So think about that plane. Okay, it's determined by a set of weight parameters. You can take that those weight parameters, you can multiply them by 10 and get the same plane. Okay, so yeah, lots of problems. Magnitudes don't matter so much. Typically, you'll use this on small problems. That being said, weight parameters are scale dependent. What do I mean by that? And this will be very true for neural networks as well. Your input parameters, if they are not of the same, or your input variables, if they're not of the same magnitude, that can cause learning problems because you'll have some small inputs, some large inputs, which mean you'll have some small weights and some large weights, and the updating scheme will now have to adjust to that. What you want ideally is for them to all be on this same or similar scale. Okay. But for neural networks in general, you will typically massage your data first before you plug it into the neural network anyway. So you will scale things appropriately. Because which you guys know a lot about optimization, and you will after this course. You won't be making those mistakes. Okay. Fine, that's perceptron. And now, it's quick one, I'll show you something. And then we'll take a break. So I put this paper up. So this is the Woodrow and Hoff paper from 1960. Very interesting. As you see, this page is unclassified. So this was classified stuff back in the day. Oh, it's not. Come on. There you go. Okay. Cool. So this is very interesting stuff. You see the classified stuff. This is from, where was this? I don't know, some big weeks, whatever. So very classified stuff, but this is really cool. This is adaptive switching circuits, and I'll show you now. This is really the multi-class perceptron, which follows a very similar algorithm. It's just for when you have more than one class. And in fact, the very interesting thing about that algorithm, if you read this from the textbook, is the reason the multi-class algorithm works is that you can write the multi-class algorithm as though it was a single class algorithm, and then all of the proofs and everything follow up. So all of the results for the multi-class case applies because it applies in the binary case, the class case. And really what they did here was they built physical actual machines, which does this. There you've got your neural network. And then there's your machine, which does the neural network. Those knobs and dials are the weights and stuff that you can change. And this physical machine would do the prediction. It's not like they coded this thing. They would find the tuning parameters, I guess, on the knobs to get the behavior that they wanted. Okay, so some really, really clever chaps working on this stuff. Now imagine you had to code a neural network like that. Okay, pretty interesting stuff. And yeah, this was the multi-class perceptron algorithm. They talk about the circuits and switching there. Look at these problems that they're working on. Does that look like digits? Little pictures? Sort of close enough. T's and G's and F's. Okay, very small, very low resolution pictures. Here you can see they talk about accuracy, so they've got these sum of squared errors that they're working on, and then some achievable accuracy that they get as a function of the number of input patterns, so the number of observations they have. Lots of technical stuff. Here they talk about derivatives. Here they talk about optimization. Okay, so again, you see these ideas are pretty old, but yeah, brilliant stuff. And you can see why these guys were excited, because now it's not only coding a neural network to do the thing, you build a physical machine, you give it a picture of a dog, and then it spits out a light that says, yes, this is a dog or a cat or something like that. Okay, so very interesting stuff. You can go read through this paper. Oh yeah, here's some other problems that they work on. Dice. Very cool stuff. Cool, so we take a quick 5-minute break. Yes, okay, 5-minute break. Let's kick off again at, let's make it 3 minutes past. Yes?
So interesting.
Why? I guess they were probably working in some think tank, and their funding was said that you do research on this, everything that you do is wrapped up in tape, doesn't get published. A lot of research works like that. We've got a colleague in cryptography, for example. She can't publish any of her work because it's cryptography. I think after a long period of time, things get declassified. Yeah. Yeah, exactly. At what point is it just common knowledge? By the time this was declassified, that was probably already common knowledge because someone else would have built the same thing. Something. Oh, in the stats department? Sure. Look, there are lots of like NDAs and stuff that you sign when you work with outside people. Our department, we don't do much that's classified. The reason for that is our university has a very like open policy. So about publishing things, we try and keep things as open as possible. Other universities have like standing relationships where like their honors projects are tied to a bank. And then what they would do is like I'd be your supervisor and you're sitting at the bank, you're working on their data, on a problem that they're working on, and I'm supervising you. You do the project, it gets marked all internally, and then it never sees the light of day. Same with masters, yeah. That's great because you get funding from these guys, huge amounts of money. It's bad because you as the student don't ever get to show anyone your research. And in fact, this happened recently. There was a student emailed me, so I want to do a PhD in this, I've got these great ideas. I'm like, excellent, show me your masters. Which is what everyone that actually knows what's going on in the world of academia, or if you want to work in a think tank, whatever, the first thing they're going to ask you for is not your marks, not your degrees. They're going to give me your master's thesis. That'll tell me what I need to know about you. Okay. Now he says, sorry, I need to quickly check if I can show you this. He goes back to the bank. They say, sorry, it's under NDA. I can't show you. I say, sorry. Because now I can't judge whether, I don't know what the quality of the research is. I'm sure the person that was supervising him was good. I know all my colleagues there, they're brilliant. But that doesn't mean you're going to have to carry the can for your PhD.
That's when you go, I can't show you that. If you meet me, I can't. I happen to leave my phone open on the table.
And the problem with NDAs are, like, industry, they're always like, yes, we want to work with you guys, we've got these very interesting problems, and he's like, yes, we want to work with you too. And then at UCT, how it works is we can't sign as a department a contract with a third party. It has to go through UCT Legal. And once UCT Legal sends that document to their legal team goes, and you spend a year long trying to figure this thing out, and it won't happen. Because there's a difference between what is said and what's written on paper, and what's written on paper is the contract. And if they see this has to be published within 2 years, like the best we can give them, I think, is a 3-year like embargo. And they see that, they're like, no, this is uncompetitive, whatever. We have a consulting unit, yeah, and then they can do consulting and stuff like that. But then again, that affects, it's not a 3-year embargo thing, but also unless you're working under NDA and you have a contract, then yeah. For our students, typically we want our stuff to go out there. So this is why our department has been doing well for many years, because we have been able to publish openly. So speaking in terms of publications, we're doing great. In terms of sourcing money from industry, but